Hello, welcome back. I hope everybody had a good break or did what I did and caught up on all the stuff that I didn't get to in the first half of the semester. So we talked about stars before the break, how they live, how they die, and when we get to the smallest stuff, we really get to something that feels almost still a little bit out of science fiction, exoplanets. Planets around other stars, so not just our own solar system. I really feel like exoplanets is like I'm an extragalactic astronomer, which basically means I'm an astronomer of all galaxies except our Milky Way, which feels like describing myself as I'm a biologist, but except for the giraffes, right? It feels very weird, but exoplanets is sort of the same thing. Before we get into it though, has anyone actually seen the eclipse of the lunar eclipse? How was it? I mean, I slept through my alarm. So
it's pretty okay.
We had a lunar eclipse where we have the sun, the earth, and the moon. In 2024 we had the solar eclipse, and never be in this situation. But unfortunately I have astrophotography friends, and so they made this like little clip here. But the best one is, let's see if this actually plays. As it goes into the shadow of the earth, you can then take a picture as the whole thing turns red. Has anyone seen the red, the fact that it looked red, right? So I wanted to, because hey, physics experiment, right? This is a live physics experiment right in front of our noses. Why does it look red? And that's because the light that goes through our atmosphere gets scattered, and the light that goes, the sunlight that goes through our atmosphere, blue light gets scattered by the atmosphere preferentially. This is why the sky is blue. It's literally sunlight that is scattered down, that has basically bounced off an atom in our atmosphere and bounced down. And this is also why sunsets are red, for example. Has anyone watched the sunrise/sunset at some point? Right, they're red, and especially if you're downwind from a refinery or coal plant, they are red because little particles of dust redden your light. And so this is, if the light goes through the atmosphere of the earth, the red light continues on, the blue light gets scattered, and so that's what we see as the blue sky. So the little bit of light that did fall onto the moon, that was the red light that managed to get through the atmosphere. And if you were like, well, what does this look like from here? It's a little too bright, so let's see if I can technically operate the planetarium on my own, but as Drew is happy to point out, not really. The moon's right here, if you can still see it. So what happens if you have a lander that's on the moon, and we do, the first commercial lander has landed on the moon and not fallen over, which sounds flip, but it is harder to do than you think, right? This was the thing that NASA worried the most about when they were landing the astronauts on the moon. There are big rocks there, and you don't know until you get there if you're going to hit one. And so it was quite important that the spacecraft landing was under control of the astronauts. So this is what it looks like. This is the Earth blocking the sun from the moon, which I think is a pretty freaking awesome picture. So yeah, from the surface of the moon, you can actually see this eclipse. And so pretty cool, we have an eclipse. I totally like eclipses. If you ever have the opportunity, go see a total solar eclipse. Do not take 98 or 99%, go for 100% and see what that looks like, because you get basically this kind of view. This is a diamond ring, so right after the sun starts peeking through, you can sort of see the sun perfectly covered there. Okay, so what is an exoplanet? Does everyone still have their little voting cards? A planet at the outer edges of our solar system, a planet expelled from its parent system, any planet discovered outside our solar system, a planet that people thought could exist in our solar system. Voting in 1, voting in 2, and voting in 3. Welcome back. I've woken everybody up with a vote. This is majority C, any planet outside our solar system. What's a hot Jupiter? A cocktail, a phase Jupiter goes through, a Jupiter mass exoplanet close to its parent star, a whole section of Roman mythology. Voting in 1, 2, and 3. Nobody voted D, no lot, okay. Yes, it is a Jupiter mass, so it's a really big exoplanet close to its parent star. Around what type, maybe you can remember this, what type of star were the very first exoplanets discovered? This is in the video. A sun-like star, a brown dwarf, a red giant, or a pulsar? So 1, 2, 3. This is just, you gotta know it if you notice it. See a lot of D, excellent, yes. Weirdly enough, a pulsar. Because pulsars rotate and give this radio blip off, you can actually see those shift in radio. So if there's a Doppler shift going towards you and away from you and away towards you and away from you, you can notice that it's actually orbiting something else. And so they found a pulsar that had 3 planets around it, but we're still not sure if those planets formed after the whole thing turned to pulsar or if they survived the explosion of the star just before it turned to a pulsar. So does that count? Because you're basically bathed in magnetic fields, X-ray emission, and you're around this, rapidly rotating pulsar, and everything else is super cold. So it's really hard to say whether or not this is a valid, those are really good exoplanets to be on. So here's oh boy, it's really dark. Here's Luke looking at the two. Who has seen the original trilogy, Star Wars? I'm sort of going like, this is no longer a geek question. You've all sort of seen it, right? Okay, so there's like Tatooine with the 2 suns that he's staring into. Can a place like Star Wars Tatooine be real? Voting 1, 2, and 3. I've got majority yes, with a few dissenters. No, we've actually found a place with that is orbiting a multi-star system. So as long as you're far enough, you can have 2 suns rotating and then basically orbit around that pair. And we found some planets like that. So exoplanets come in all kinds of sizes, come in all kinds of places, and come out in all kinds of combinations. So this is a big difference. So this is something that has changed in my lifetime, which means that I'm full of wonder and excitement about it, and this hasn't changed in your lifetime, so you're probably going a little bit, yeah, this has always been this way, right? It's like the internet. So when I got started, we had one solar system to base all our knowledge on stars and, and planets and how planets form on, right? We knew a lot about those planets. We've actually visited some with robots. We actually took samples, had a look, but it was still one solar system. Speculation on whether or not there could be other solar systems has been around for hundreds of years. So, 17th century, right? People with big wigs going like, oh, well, there must be, it's perfectly capable if those stars are other suns that they should be exoplanets there. The naming convention is a little funny because we have words like Rigel, we have Betelgeuse. So if you find something like around Alpha Centauri, you have the capital letter, those are the 2 stars. And if I find a exoplanet around it, then it is like a lower capital. So the naming convention is Alpha Centauri B, that's the star, B, that's the planet around that star. Not yet discovered, right? So that's something. Never, ever, ever, ever let the internet name anything. So there was a thing where we went from, well, let's involve everyone in the world and see if we can come up with some cool names. But this is sort of after the filter, so never, ever let the crowd do that. So we sort of stuck with like just this naming convention where we take the star and we say B, A, B, and C. Okay, so. How do we find these things? How did our technology suddenly get so good that we could start doing this in my lifetime, effectively? When I started with undergrad, 1995, yes, I'm that old, the very first one was discovered. So this was a thing where it's like, I'm an astronomy major. They discovered what now? So that was really exciting. But there are a few things, there are 5 different ways that you can find it. So initially we didn't know which one was going to work. The first thing that you want to do is direct imaging. You want to take a picture of this thing. But I'll tell you why that's hard. Transit method, it's basically eclipses. Radial velocities, it's Doppler shifts. Astrometry, it's shifting on the sky. And microlensing is a gravitational effect. So let's dive in. Exoplanet detection, type 1. Direct imaging. Finding exoplanets the hard way. So we're going to take a picture of the Earth or Jupiter, but we're at a completely different star. So you can imagine you're now looking at a different star, and the star is the bright thing in the whole solar system. The sun is the brightest thing in the whole solar system. You're now trying to find a gnat right next to it. So you have to block the sun out and look for something much, much dimmer. So the parent star is very bright. The planets are often very close to that star, and you're basically trying to see a firefly right next to a searchlight. You're looking down the beam of the searchlight, and you're trying to find the firefly from miles away. So this is hard, but not impossible. So the thing that you do is you block, you have something in the telescope that blocks the main star, so this is where Beta Pictoris is, and Beta Pictoris B is that one planet right there. And so just to give you an idea, this is Saturn's orbit. So basically this is sort of a Saturn on around a nearby star. As you can imagine, this is the disk, the protostellar disk. So this is where new planets are forming around Beta Pictoris. And so here's one of those that were found. So it's relatively easy to find if the star is dim or they're nearby. And it gets better in the infrared because, again, planets glow in the infrared. They don't really reflect much light in the optical. So yeah, you see a little blob like that, but it could be a little side effect from blocking the bright star, right? And so you have to go back and see if it actually is still there. Or for example, Fomalhaut is another nearby star. You actually see over a few years, you see this little blobby move, and that is very likely just formed exoplanet. So yes, it works. Yes, you can do that. But as you can imagine, you have to block this out. You have to make a very specific instrument for that. So you block the light perfectly around the star. Well, it still leaks out, and then you have enough information left to see little pieces of the solar system, of that solar system move. So for example, from 2009 to 2015, I think, you see these three planets move. It's sort of Jupiter and beyond, right? This is 20 AU. So this is the entire inner solar system. It's going to get really tough to get something like our own Earth on a picture like that. It works better for a big exoplanet far away. With me so far? Works for just a few stars. There's just a new one out. I forgot to put it in. I'll put it in for Thursday with James Webb. This is the hardest thing to observe. You have to block that light out perfectly, and then you see a little blob, and then you have to come back, 5 years later to see if the little blob moved. Because it's so far out, the orbit is like 70 years. So you have to wait half a decade for this blob to move a little bit. If it didn't move or disappears, then it wasn't an exoplanet. So it's a hard process to get these things. But the neat part is you immediately can see where they are, what they do, their orbits, and you can even get a color. So this is the goal for NASA, for example. We have a new mission that's currently being drawn up. It's not even on the drawing board yet. So we're basically putting requirements together, but the main requirement is probably in the title, the Habitable Worlds Observatory. It is going to look for these things. It's going to find little blobs like that, but they're going to be the equivalent of our Earth. And then we're going to see what they're made of. All right, second way to do this, transit methods. What about eclipses of other stars? So the trick is, I have a star, I'm staring at that star, and a planet goes in front of it, and it blocks ever so slight amount of that parent star. So it's blocking a little bit of the light. So if I could measure the light coming off a star very, very precisely and do that over time, I can watch this thing basically go across. I just see this as a point, but I see a little bit less light, and as it moves away, it comes back up. So not only that, I can do that for one planet, wait around, and there's that system's Jupiter. It's deeper because it's a bigger planet. And so I can watch these things go by, see how fast they transit, see how deep that curve is, and I can wait around and actually see if that curve, that dip happens again. So as long as I can measure the brightness of a star very, very, very precisely, so I want you to notice this is 100%, this is 99.2%. The entire dip is not even a percent worth of dimming. right? It's not like the whole star disappeared for a second there. It is just a little bit dimmer. But you see a red curve, you see red points and black points here. These are separate teams, and you can also re-observe later and watch for this dip again. So if you carefully model this, it gives you an idea of the size. If you know how big those stars are, you can actually see how long it takes them to transit and the relative size of the disk of the exoplanet. Okay, so that is actually a very good way to do it, and you can even do it with a small telescope, as long as it can measure the star's brightness very precisely. All right, third one, exoplanet detection number 3. This is how the first one was discovered. Radial velocities, the case of the tail wagging the dog. So in this case, we're down here, and the exoplanet and the star orbit each other, right? We're not just orbiting the sun. The sun is also moving back and forth ever so slightly because of the orbit of the planets. Now, you won't notice the Earth's motion much. It's a couple of centimeters. Like, we move the entire sun maybe an inch or less. So it's not moving a lot, and it's moving an inch every 6 months, so it's not a big movement. But if you have something like Jupiter, yeah, you have a bigger movement. But it's still, it's all a slow movement. But if you take something like Jupiter and put it close by, and then it orbits each other, then you can watch, the sun move towards you and move away from you. You go like, well, this is probably easier with a little GIF. If you're wondering, this is the European Southern Observatory. They made a whole list of these things. So we're watching the Doppler shift of this star as it moves towards us, and now it's redshifting away from us as the planet comes towards us, and it's coming towards us, it's blue shifting. So you get a blue shift, a red shift, a blue shift, a red shift, and the pattern repeats. That's another important one, right? I can go back with a different telescope and actually observe that Doppler shift. So I get red shifted, blue shifted, red shifted, blue shifted. I alternate between those two. With me so far on that? Doppler shift? I know, beginning of the semester, back of the mind, but yes. So, the radial velocity in meters per second, which is fast if you're in a car, but not in space, so the speeds are much higher. And so this is 51 Pegasus B, and you see this is basically many, many times that they watch this transition. So it's redshifted, and then blue shifted towards us, redshifted, and the pattern repeats itself. So you can measure, if you know how heavy the star is, you can measure the mass of the planet. Third one is astrometry. So again, we're wagging the tail, the exoplanet is moving the star. So in the plane of the sky, now we're looking on it from where you're sitting, right? We're looking on top of the solar system. We're now seeing that the star moves down a little bit and up a little bit, and down a bit and up a little bit. So if I know exactly where the star is, right, really down to the milliarc second, we can actually keep track of something that's wobbling like that. Now, that wasn't really a possibility, but Gaia, which just stopped, can actually do that. So if you have a wobble like this, where the star is moving back and forth because a planet's rotating around it, and I compare its position to its nearby stars, and I notice that it does this little circle on the sky, I can infer that has a exoplanet. So we've been finding some exoplanet, or confirming some exoplanet that way. Yeah? All right, that was 4. And 5 is gravitational lensing. Now this is the mind bending or mass bending or light bending way to do it. If I have a star, it bends the space around it, so there's a little divot there. And the lights go out, and here's another star system that's moving between here am I, and then as it's going through it, it bends the light around it. So briefly, I see that star become brighter for a second, because it lenses the light around it. And not only that, I'm showing that again, because it's a strange thing. So we've got a distant star, we're just keeping a watch on that star, maybe a whole bunch of them, and as a star with a planet goes by, it lenses, it briefly brings all the light to down here where we are. So it briefly becomes brighter, and because it's not a perfect lens, because there's an exoplanet in there, you get it becomes brighter, but there's a little blip in there. So, yes, we tried to do that, and it worked a couple of times. The trouble is, then that whole planetary system has to go in front of another star for me to confirm it, and it rarely does. So it's either you caught it or you didn't. It's not repeatable. Okay, I'm looking at a star, I'm measuring its brightness over time, and I'm watching something go in front of it. And as something goes in front of it, it becomes dimmer. What is that? Direct imaging, transit, radial velocity, or lensing? Voting in 1, 2, oh come on, come stop, 3. I feel like I need to talk to this side. You're all confused, they all got it right. So I feel like I need to stand on this side and yell louder, maybe that helps. So this is it. The cat transits in front, right? It's a transit detection of the whatever it is, right? I mean, this is instructive as in we don't know what the shape is. So if a cat transitions in front of it, it would still look like that. But we sort of assume that most of these are planets. I'm going to keep going a little bit longer. So the very first one was in 1992. That was a pulsar. Again, we don't know whether these things formed afterwards. So it didn't tell us much of how planets form, other than one extra data point is always, if you have one data point, it's the solar system, and you get one other piece of information, that tells you already a lot. One, planet seems to come in groups. This was 3 planets, not 1. 2, if even they occur around a pulsar, which is not the friendliest environment, they must be pretty common. So this gave us all hope that we could find more. And the first confirmed exoplanet was 51 Peg, the one that I showed you, with that radial velocity. They built a specific spectrograph that could measure the motions of stars towards and away from us, and they just sat on a couple of nearby stars long enough to measure its radial velocity. Now, stars do a lot of things. They pulsate. We saw Cepheids. They pulsate. So it's very hard to figure out if that's the pulsation of the Cepheid or it's the planet around it. So you try to find a nice quiet star, like our sun, and see what its velocity does. There's a great story around this because there were 2 teams. The other team also thought they had found a exoplanet this way, except that their period was this between peaks was exactly 6 months. And it turned out that they hadn't quite taken out the motion of the Earth around the sun. And once they did, it disappeared. So the first team came up and everybody was excited because they had said like, oh, everybody gather around, we're having a press conference. And so they had to go up there and say, I'm sorry, we checked our work and it turns out we didn't take the Earth's orbit out correctly. And then this team came up, which was the Swiss team right after, and was like, and we found one. And so there it was, because this is only a few days, so this wasn't the Earth's effect. And so this is a hot Jupiter. It's a massive exoplanet compared to its parent star, and so it shifts the parent star around quite a bit, and it's close enough that you can do this in a couple of weeks, because it repeats very, very quickly. So we found the weird stuff first, right? We found those strange, because we originally didn't think that something like the size of Jupiter could form that close to a star. It would get blown apart or something during formation. And so what you then do with the transit method is then we realized that we could actually measure from space the flux, the light coming from the stars very, very precisely. So if we launched a dedicated spacecraft that just looks at stars, watches them dip, and then basically wait for the dip to reappear. So you have to do patient spacecraft, but you wait for the dip to reappear, wait for the dip to reappear. And if you don't have time to wait for the dip to reappear because your spacecraft has to look at something else, you actually have people from the ground actually waiting for the dip to reappear. So lots of people have done these exoplanet searches. So this is, for example, a test field. So when we do this on the dome, do the all sky version, you see like there's lots of discoveries in here because that's where Kepler, the very first mission, looked at for a very long time. If you can find Vega, this is where one of the Kepler fields was. So we have lots of exoplanets discovered there. And then we launched TESS, and TESS is basically meant to do the nearby ones, to do the whole globe. And so this is hard to do from space. Space is easier to look at a small patch. Hubble looks at an incredibly small patch of the sky. So if you now want to look at big chunks like this and look for exoplanets, especially small ones around the nearby stars, we need to do that with a camera that is good at taking a big chunk of the sky, and we actually make 4 of those. So this is 24 degrees, and remember that this was 10 degrees, so it's 2 fists on the sky, and then 2 fists like this, and we have 4 of those. So it's taking basically a whole chunk like that, looks at that for a month, and keeps moving, and so we look for those transits with TESS, and then it moves over to the northern hemisphere. It's been doing that for about 6 years now, so it's covered most of the nearby neighborhood. And so if there is a Earth-like star around a nearby Earth-like planet around a nearby star, that's the sentence I wanted to say. An Earth-like planet, a little rocky planet around a nearby star, because those are the ones that we want to look for, because then we can look at it with this. And this is this can do all the nearby stars, but we want to find these Earth-like planets. How cool would it be to find? I think it's cool. I realize that my idea of cool is different than your idea of cool, but I think we can agree that if you find something that looks like an Earth around another star is kind of important for humanity. Just the knowledge that there is another Earth around that nearby star. That is something that we could potentially send a robot to, or generations from now send even people to, although that's the realm of science fiction. The fact that you know where to go would be already a big breakthrough. So TESS has been looking for lots of these, gets all these other things as well, but it's been looking for these stars. And so the catalog has been going up steadily, and I have switched to the NASA one. So the exoplanet catalog now has almost 6,000 confirmed, so often through two different techniques. Because if you look at the transit, and you see a transit, and then you go back with the spectrograph, and you see the planet move back and forward at the same frequency, you go like, oh, 2 different techniques, both confirmed, that's that exoplanet. If I go back to a different telescope, if I go back to radial, I can go back to the guide and actually fish out the astrometry and go like, yep, it actually is, I can see it wobble back and forth, and it transits, great, those are 2 different techniques that confirm, right? So in science, you always have, in science and journalism, 2 independent sources is the gold standard. So if I have 2 independent teams, 2 independent telescopes, or 2 independent techniques, preferably a mix of the lot, but I have 2 separate voices saying this happened, it's here, same thing in journalism, then you have a confirmed exoplanet. So these are all confirmed by either a secondary team seeing the transit, or a secondary team seeing the radial velocity, or a combination of these things. Confirmed, we know that they're there. And so this started with Kepler, expanded with TESS, and so the star count is lower than this. It means that there's this many planetary systems. There's at least 1 around each of these stars. And so the neat part for me is that exoplanets come in all these different sizes, because from the transit we can tell how big they are. Also distances, right? Sometimes we see the slow transit, it means it's further away. And so we've been finding just an absolute menagerie of exoplanets. And just to give you an idea, this is what came out of TESS. So the easiest thing to find, like, here's our solar system. This is the inner solar system, and is this the inner solar system? I think this is Jupiter, if I remember correctly. So So a couple of things. One, the easiest ones to find are the ones that repeat quickly, right? I can look 3 days later and whoop, there is that transit again. So we're biased, and it's always good to recognize in science when you are biased in your detection. Our technique is, by definition, transits are biased towards ones that repeat quickly. I can confirm them a week later, rather than with Jupiter, it would be like 70 years later. Right? So I can find ones that whip around and are close, therefore close to their parent star. So the majority of the ones that I found, is everybody mesmerized by the wobbly things? I am. I've watched this for a while before I actually do my class. All right, so the neat thing is, first we know that, okay, we're biased towards things that are small, orbits that are smaller than our typical solar system. Okay, fine. And we know that some of our stars are hotter than others. So we can give a first idea of how hot the surface of these things is. Red is lava, yellow is the surface of Venus, which melted the Venera. Mercury is already hot, and Earth is blue. Okay, there's a lot of the floor is lava out there. There's a lot of exoplanets that are so close to their sun, they're almost, they're being baked. That's fine. I'm seeing some blue though. So there are already, in the planets that we've found so far, ones that could have liquid water, ones that are at least cool enough to have something like that. Typically, they tend to be a little bigger than our Earth. They're easier to spot. A dip that is like, whoop, a nice big dip from a Jupiter-like size thing, yeah, that's easy to spot. If it's just a diddly Earth, it's a much lower dip, so we don't get as much of a signal. So we have to repeat that and check it. Okay. Now is a good time for group work, because I have now talked enough at you, and I've talked all through all 5 ways to detect an exoplanet. So this is the transit method, which I think is the intuitively, like it's an eclipse. These things block the sunlight, or the light from the distant star a little bit. And I haven't tried this yet, but I got a robotic telescope for my birthday. But it is a small one that you can just steer with your phone. It's pretty amazing. But you can actually do exoplanet flips, this stuff with it. You can actually do a transit and see if it dips. I know dip means something else, but dip here means it gets a little dimmer. Sure, you know the deal. Oh, yes. How does it feel like Monday too? It's my first class since the break, and it feels very Monday to say the words, but I hope everybody had a good day. Just to give you an idea, let's find diff. see it out.
But I think it's like as opposed to just basically separate. So it would take time. Like it stays in front of you for a certain time. And it's like, why is it a line as opposed to a point? For a point, it would be for like a second there's in front of the person. But if it's at a line, it means that it's like in front of it.
That's great.
Stop, cover, yeah.
So direct pictures are, but finding these little dips can be very easy, especially if you can do it with little telescopes that people can just buy, and or if you have dedicated space stations. So finding these little dips as soon as we had something. You all grew up with these cameras getting better and better and better. It still blows me away that a colleague of mine actually took a picture of Uranus with his camera. We needed an actual dedicated telescope to discover the thing in the 19th century. He took it with his phone. Okay, these things have become so sensitive that yeah, these little dips, totally doable. So as long as you have a little telescope to stare at your star and you notice a dip like that, and you notice that dip repeat, then you can learn a lot. And so the majority of exoplanets have been found using transits, either with Kepler or TESS or a combination of TESS and follow-up observatories. And those follow-up observatories include our own observatory here at in Louisville. We have one here north, just out of 71st. There is a small observatory, and one of the things that we do is follow up when Tess is looking to the next sector to actually follow up on the dip that he found in the previous one. So you can find out a lot of things when you see that dip occur, right? So if I know when the time between dips is literally the period of the planet. That's how long it takes for it to orbit once. Well, guess what? We learned about Kepler. That rule still holds. If I've got the period, I've got the average distance in the sun from the sun in AU. I've got the average distance of this planet from its parent star. That's useful because that tells me how warm it is, right? How is it nice and warm and cozy, or basically is it so cozy that the floor is lava, or is it too far away and it's a ball of ice, right? So the period already tells me a lot. So we have Kepler's 3 laws, but we also know that all planets orbit on ellipses. So am I seeing it here when it's close by, or am I seeing it here when it's far off? And I can see the whole period, right? So I know when the dip reoccurs. And so I already have the average distance. But I can also see how fast it goes along, like, oh, the relative size first, right? I know, if I know how big this star is, and I know how big the dip is, then I know what the relative size of the planet is. So I know its radius. I know if it's a big puffy planet or a small rocky one. So I got the relative size, and we put a lot of effort in measuring the sizes of stars nearby, so we can actually say the absolute sizes. This gives me the width of the planet. How fast does it transit across, right? So how fast does it transit into and or away from the disk? It also tells me how fast I transit on this part of the orbit. So if it's on this part of the orbit, it's slow, and I can compare that to the whole period. Or is it on this side of the orbit where it whips past? And like, oh, it's a very elliptical orbit, or it's a very circular orbit. So I can figure out if it's a circular orbit or an elliptical one, and I can see how big it is, and I can figure out maybe what the mass is, and that gives me a density. So I have a density, I have a size, I have how stable its orbit is, how warm it is, how much temperature it's getting, how much heat it's getting from its parent star. That's a lot to know already about an exoplanet. So that's how we got that orrery. By the way, that mesmerizing wobbly thing, that's called an orrery. I love the word, but you don't have to remember that. It's just the model of all the planets moving around a star. So, for example, if I'm looking edge on, like this thing is going in front, I'm looking at the edge of this system. How could we detect this planet? With direct imaging, with radial velocity, Doppler shift, with transit, or all of the above? What do you think would work? 1, 2, 3. It's the majority D. So let's see, direct imaging, yeah, it's all the way out here. When I get lucky, I might do that. Radial velocity, yep, it's moving the planet back. The star is wobbling back and forth with the exoplanet. Transit, yeah, it's going in front of it, so I can see the transit. So all three would work. And basically, I could, for example, if I find it in transit, I can find it with radial velocity, confirm it with radial velocity. Separate confirmation. Right? This is the gold standard in science. If you have a separate, completely different method that also confirms your conclusion, that's the gold standard. That would be fantastic. If I then also manage to snap a direct picture, great. You're piling on at this point, but that would work. Can I do direct imaging, radial velocity, transit, or all of the above with this one? I'm looking at top down, right? I'm looking at it's orbiting like this. I'm looking on the north pole of the star. Can I actually detect it with all of these techniques right now? W1, W2, W3. All right, you know the drill. Talk to your neighbor, even if the two of you agree, and explain to them why your answer is correct. You may have to find a neighbor to get 90 cents. Go again. 1, 2, and 3. I get majority A. Yes, we can do this with direct imaging. That's what we saw, right? We saw this from the top, and we saw the little dot move, and if the dot moves 5 years later, then yeah, that's direct imaging. Radial velocity, it's not moving towards you or away from you, correct? And it's not transiting in front of it either. So we're biased a little bit to only the ones, the transit method, to only the planetary system we're looking exactly edge on. You have to have that planet go in front of the star, otherwise it won't work. So if it's just a little bit like this, or even like this, I don't see a transit, so I'm biasing myself in all kinds of ways. So this is something to understand, because if you are doing an observation, and astronomy is an observational science, a social science is most of the time an observational science. If you start experimenting on people, other people are going to come knocking, hopefully. So you can only look. So if you do social science or astronomy, you can only look. So you have to understand where your observation, your vantage point, is biasing your result. If you don't take that into account, you go, that star has no planets around it. Does it? Or maybe it doesn't transit. Or maybe it doesn't move it in your direction. So you need to know how many, if I see half the planets have a transit, or half the stars have a transit, what does that mean for the ones that don't have? So understanding your biases is important. Now here's the extra special reason that we would like to have transits. Because what you just saw with the lunar eclipse, you saw the moon turn red because the light went through the atmosphere of the foreground atmosphere's planet. The planet's atmosphere, sorry. Atmosphere's planet, that's not a thing. Okay, so I have the light source. The light is going through the atmosphere of this. There's a little circle of light going through the atmosphere. So if I can measure the spectrum of this star with and without the exoplanet in front of it, I can see what is happening to the star's light as it's going through that atmosphere. And so this is the part where I think this is just science fiction, really, where we're going to look with the James Webb Space Telescope. We're going to look at, for example, this is the sunlight at the top of the atmosphere. This is the sunlight as it gets down to our atmosphere. So this is what the atmosphere does. There is oxygen, there is H2O, water, more water, more water, more water, CO2, and more water. And so basically, if you've got water in your atmosphere, it's going to block at all kinds of wavelengths. It's also blocking here at oxygen 3. What's oxygen 3? Just checking if there was a chemist in the room. Ozone. That weird smell if you're doing a photocopy. Photocopiers smell weird, right? Am I the only person who goes, ugh? No? Not just the ink, it's ozone, right? Ozone comes off photocopiers, but also we have them in a higher atmosphere, and that's great because it's blocking the really, really blue ultraviolet light that turns our skin pink and or burnt and or cancerous. So it's great that we have an ozone layer. That's the ozone layer. So basically, if I have ozone, if I have oxygen, if I have water, I'm definitely seeing that. But I'm also seeing CO2 here, carbon dioxide. You know, the stuff that we breathe out, the plants absorb again. We'll get to the whole effects of carbon dioxide as well. But we want to get all of them, and we want to study then the imprint of what is here, right? So we want to compare the spectrum as the stars, the planets behind it, and as it's in front. So since I know when that dip occurs, I can take a really powerful telescope and take a spectrum both before and after. And so you can start thinking about like what kind of atmospheres do these planets have? And these are all artist impressions because you just have to tell a space artist, we found a planet around a double star system, and they'll run with it. And the results are much prettier than our little dot or maybe a little dip or something. So you get things like Gliese 667cc is a potentially habitable planet in a triple system called Gliese 667. Right, so you've got a triple stellar system and planets orbiting around it. Now, I told you about, like, depending on how far away you are from the parent star. So it depends on the kind of star. Here's the solar system. If you're at Mercury or Venus, it's too hot, right? We're too close to the fire. If we're here at Earth, nice and cozy and warm. If we're a little further, Mars, frozen solid. So there's sort of a perfect zone to be in. It depends on the kind of star that you're circling around. So what did we call this? It's not too hot, it's not too cold, it's just right. What does that remind you of? One hint, bears. It's the Goldilocks zone. It is just right to have life in there, or at least water, right? We're sort of assuming that most life in the universe likes a planet like ours. If it's silicon based, it needs freezing temperatures. we're out of luck, right? We're sort of looking for the equivalent here. So we're looking for something that's the same size, same composition, and warm enough to have liquid water. And so we have these fantastic terms because like every team comes up with these names. This is TRAPPIST-1. It is so this is the inner solar system, again with Mercury, Venus, Earth, and Mars. TRAPPIST-1 would fit somewhere between, the orbits are like all the way in here. And like, why is it it's somewhere between our inner solar system and the Jupiter system? Because the star that they're orbiting is an M-dwarf. It is a very piddly, faint star. But there are 7 rocky planets around. And you can see, like, because it's so small, they orbit so fast that we actually see the dips repeat. Here's the fun part. 2 of them are too hot, and 2 of them are too cold, but basically all 3 of them the 3 in the middle are good. Could have liquid water. Think of this as Antarctica, think of that as the tropics, but somewhere in between. Like, they're all liquid water amendable. And if you happen to know, Trappist is a Belgian beer type, and this was also a Belgian team that found it, and so they've been calling everything after either beer or speculoos. So it's all food-based with these people, but it's been entertaining to watch that, right? So what's the difference between an Earth-size and an Earth-like planet? Public relations, it means the same thing. Mass, the same size does not mean the same mass. It is in the habitability zone or A, B, and C combined. What do you think? Earth-size versus Earth-like. Just curious on your opinion. Majority of you think D, like it has to be the same mass, because otherwise we can have something Earth-sized, but if it's made out of hydrogen, right, it's not going to be heavy enough to actually have the same gravity. If it's not at the same good right distance, it's not going to have liquid water. All right, I usually have a Halloween lecture, but not this semester. But the conditions has to be sort of conditions hostile to life, like a lake of lava, like the floor is lava. That won't work. We just use this guy all the time when it's, the first thing people say, like, oh, it could be aliens. Like, please stop. It's usually something weirder than that. But let's look at that. So the habitable zone is like, we found the most Earth-like exoplanet yet. This is a repeating headline because we keep finding similar masses, similar size, in the right temperature range, but we can't tell if it's rotating around. It could be tidally locked. We can't tell if it has an atmosphere yet for most of these. We're working on it. So it's habitable zone, habitable-ish, the survivable zone, right? So we hope to look for biosignatures in the form of screening. The reason for that is that if we have a bunch of these candidates, we've had them for a while. We've had super Earths, like bigger than, quite a bit bigger and quite a bit more massive than our Earth, but the same size has also occurred, and in the right temperature. So yes, we've been following these up, but this is driving the next generation of telescopes. So I didn't do a thing about telescopes this semester. I just want you to admire this graphic at the moment, and then I want you to find the Ford 150 down here at the bottom. We got ambitious. This is a football field across of glass. It is, and if you think this is completely science fiction, you are all out of your noggin, dear astronomers. It's currently halfway being constructed in the Atacama, Chile desert. We're nearly there. So not only are we a little mad scientists, we also have a base. So it's getting closer that we can do this. Yes, sir. You don't. Short answer is you don't. So you may notice that it has a little pattern here. It's these are all hexagonal elements about yay big, and so you can swap them out. Everything is steerable, so basically it shapes itself and keeps itself in the right shape. And yeah, this is basically the biggest mirror ever built. It's the 30-millimeter telescope, or in the European case, is the extremely large telescope. Yes, we've ran out of superlatives and just went with it. So, And this is the 30-meter telescope on Hawaii. And so this is still a graphic drawing, but also I'll give you the cores that are down there. So we are looking at following these things up, right? And so with transits, we found these. With radial velocities, we found these. So you notice that we are sensitive to different radii and different masses of planets, but we're filling the whole place in. So just to give you an idea, this is 10 AU, this is 1 AU, this is a tenth of an AU, this is a hundredth of an AU. So we really found some that are really right up to the, snuggled up right to the the parent star. So this is the Earth mass, right? This is one Earth mass. We found lots of Jupiter-like things all the way out, and we found lots of things at all radio. We're like, not here. Yeah, that's true, but that's because we have to find those either with direct imaging or we have to wait for 100 years for the next transit. So human lifetimes sort of limit our sensitivity there, but it's coming. And so this is what I wanted to talk about today, about exoplanets. We'll talk more about exoplanets, and I'll maybe, since I've sped run through some of it today, I can maybe do a little bit about aliens or technosignatures next time. It's a really fun subject to think about. So we're trying to think about not just, for example, what our Earth looked like now, because if I look at my atmosphere now, we've got dust, we've got methane, we've got CO2, we've got oxygen, we've got ozone, we've got water. But if I go back way before the dinosaurs, right? Who here was a big dinosaur fan in their youth? Okay, excellent. I've got some people who were. My peeps. All right, fantastic. You think of longer term, or basically my case piece. So not just dinosaur train, right? We go before that. At some point, trees were invented. So before that, we had an Earth that didn't do its photosynthesis with trees. As soon as trees were a thing, you start binding a whole bunch of carbon to these much bigger plants. It was such a radical change that it was almost something that we're doing now, basically the other way around. It sucked a whole bunch of carbon out of the atmosphere in a relatively short amount of time. You can do the same thing if you have a certain kind of microbe, and they found them. There's still a colony of them off the west coast of Australia. That's the last of them, I think. But they used to cover the entire Earth. They were anaerobic, so they turned water into oxygen. So they made oxygen, so they changed the composition of our atmosphere. Life has a tendency to change the composition of its atmosphere, but so do volcanoes. Or if you just happen to throw an asteroid at it, it also looks very different right after. And so looking at what that looks like is one of the goals for looking at these Earth-like planets. We could find life elsewhere if we see the right biosignatures. And so that's what we're looking for. But that doesn't mean it's people. It doesn't even mean it's cows. It could be pond scum, right? If you just have enough of it, if you cover the entire Earth with moss, its atmosphere is going to look different, and it's also going to reflect a lot of green, like we can see that the whole thing's green. Right? So that's what we're going to look at. That's what I'll talk about also on Thursday. Biosignatures and then technosignatures. This is called the search for extraterrestrial intelligence or the search for extraterrestrial life. And really, we're interested in the life part. Because if we see this happen, we know planets are common. They're so common. Every time we look at a star, there's at least one planet around. The implication, after we correct for our biases, is that every star you can see has at least one planet around it. Meaning that probably it's more, and it's more like our solar system. The big question was, for 300 years, is our solar system special? And the answer is, not really. Jupiter-like things, all over the place. Little rocky planets, all over the place. Can you see them in young stars? Yes. Do you see them in old stars? Yes. Do you see them in dead stars? Yes. They're everywhere, right? Lots of real estate. And yet, not a single peep from ET anywhere. And so, what does that mean? Is it very common, for example, for plants to evolve, but not multicellular life? Is it?
What's think, but like, what's the point of like continuing to explore space? Like, if we go for, you know, hundreds of more years and we still don't find life on other planets, like, why do people feel so passionate about like finding new planets and stars and that sort of thing?
Apart from the fact that they're huge Trekkies, right? So I think it goes back to like, are we alone? If you look up to the night sky and you look at this just vast expanse, there is just so much space out there. There is so many planets out there in our own Milky Way, and then there's so many Milky Ways out there. It almost feels like a waste of space that it's just us. But you know, okay, fine, but that would solve the mystery. We also don't know how lucky we are, but we know that we got lucky a bunch of times here on Earth, right? If you look at the genetic makeup of humans, there was a moment where all humans was basically one little population of about 2,000 individuals. So the human race came to a pretty close near extinction event. There have been a couple of major extinctions on Earth, right? You've got the dinosaur one, but there's like 5 others. And so there are major extinction events happening. So does it mean that we just got extremely lucky? And we're talking large numbers here, right? So are we just the 1 in a million chance for life to actually manage to get past the age of 5 billion years? Or what the hint that seems to happen with Earth is like, as soon as it's cool enough, it seems to have life on it. Microbial life pops up almost immediately in the geological record. So it's like, it seems common. It seems like it had no trouble getting started. So is this normal or is this really rare? And we don't, like, the answer lies in there in between somewhere. So you can do science 2 ways. One, we find a biosignature somewhere. We find the oxygen, water, methane combination and it looks green, for example. You're like, that has to be chlorophyll. Okay, that's a plant-like, covered in plants planet. That would tell us that is a step easy to get to. But also if we sort of get a null result, what's it called in science? You say like, yeah, I didn't find anything, but I'm very certain that the answer is no for this one. You find that for all 5,000 planets that we found, for example. And we know that the odds for us are lower than 1 in 5,000. By the time we're done, it's probably like, yeah, we're literally a 1 in a million shot. I don't know, I think just like the picture of Earth from the moon, the knowledge to spread that around, right? We have now a piece of knowledge for everybody to use. Our planet is a 1 in a million. Maybe we should be careful of that planet then. I think that's an important thing. Sometimes a piece of information from science sort of makes its way to the general consciousness, and it can be a little spiritual, or it can be like we should be a little more careful with that tiny little blue dot that we're all sitting on. Because, yeah, the odds were literally 1 in a million, or 1 in a billion, or even less for us to be here. So I think that could be, is that a good answer to that? What do you think?
Yeah, that's interesting. I'm just curious, because like, I do find, I mean, I wouldn't have taken this class if I didn't find it interesting, but like, as we keep talking about like the continuous exploration, I'm just like kind of wondering, like, what's driving all of this?
Yeah, is there an end to it, right? So, well, you have to think long term, right? So we've gotten the written word for maybe 10,000 years. Like the oldest written words are from Mesopotamia. It's cuneiform. It famously is a sort of a Yelp review of somebody's copper. So it's like, bought this guy's copper, it was terrible. And it's like, yeah, we found the letter. It's amazing, like people complain in exactly the same way. There's a letter from like, students don't do their homework. It's like, when is this? And it's, you kind of go, you sort of make a connection to humans on longer scales. But 10,000 years is barely anything as far as on these scales, on the scale of the human universe. So we sort of connect up with longer scales. We didn't know that, we speculated other worlds existed for 300 years. Now we've known they exist for all of 30. That's pretty short compared to how long we've wondered about it. So that's a thing that I would say, like, well, as long as people are curious about it, they'll probably keep poking the question. And it's called the Fermi paradox, like, hey, if there's so many planets out there, where is everybody? And that is a thing to answer, right? So we'll talk, I want to have a little discussion on that on Thursday. But I think yours question is like, when do you stop? And when is your answer good enough? And that's probably a personal one. We're not done yet, we barely got started, and we barely scratched the surface with getting a good answer. Because the answer right now is like ubiquitous life on all these watery, rocky worlds to we're literally the only one. If it has to be somewhere in between, so I'd like to know which one it is. Me personally, all in between. Yeah. Thanks, good question. All right, I'll see you all on Thursday. This is where everybody rushes out the room. All right.
Everything is falling.
So